All right. I think we'll be good to start. So we can assume that everybody who is not in this room knows perfectly well how the internet works. So that's good news. But never too late to learn a little bit. My name is Alex. My colleague Peter. And we're both from Center, and we're here today to explain to you how the internet works and how the DNS works. Just a few practicalities before we start. The red pointers, like this, they indicate policy aspects throughout the presentation. For asking questions, what we would like is for you to take notes of your questions throughout the presentations so that we can address them at the end. Because very often we have answers throughout the presentation, so it will be nice to have them at the end. If you have more questions later, of course, do not hesitate to reach out to us. And another important point is this is a basic training. There will be corners that will be cut. So just to put a little bit of expectation management here. And before we start, who are we? Who is Center and what do we do? Center is the Association for the Country Code Top-Level Domain Names. How did I explain to my mother where I work and what we do was the challenge. So the way that I managed to explain it is the simplest way is when you have a URL in your browser, at the very end, after the last dot that you see, you have either a .ge or a .ca or a .com. That's a top-level domain. They are managed by registries. We'll go into the details a little bit later. The registries that manage the top-level domains, they are both either generic top-level domains or country codes. Country codes are two codes. You will recognize them very easily. First question for this audience. GE is the country code for? Yeah, excellent, that's a good start. All right, and Center is an association that represents registries of country codes in Europe mostly. And the reason for that is that since there by definition only one registry per country, because there's only one country code, the best way for them to exchange with peers is to talk to their neighbors. So Spain wants to talk to the Netherlands, and Canada wants to talk to Israel, and this is why our association exists, basically, is to exchange that type of information. We have 54 full members that are all country code, 9 associate members that include country codes that are outside of Europe, but also generic top-level domains, and 13 observers. And just to give you an idea of our membership, we represent altogether, all the registries, is about 73 million domain names, which is about 50% of the registered CCTLDs worldwide. And another important aspect about CCTLDs, we'll come back to it, is that most of our members are non-for-profit organizations. So we have, our members have this commitment to the local internet community, and that includes a lot of education and awareness. So that's also what we're doing here today. What Center does, just to give you an idea of what we do for our members, we provide and help aggregate a lot of statistics and data for them. We have public documents and documents that's also just for the members. But just so you know, some of the documents you might recognize, we produce reports for some of the big meetings that you've probably heard about, ICANN, IETF, and RIPE, NCC. And those are publicly available, so that's important to know. So what are we going to learn today? Why is this slide is important? Because there's a lot that implies there's a lot that we will not have time to cover today. So that's why we want to frame a little bit the context of what's going to happen today, so that in case you have other questions, we can address them afterwards. What the internet really looks like, what IP addresses are, how they connect to each other and how networks work, how the domain name system works, obviously, why the root is important and PTI matters. And I'm just going to intercede here and say you will see a lot of acronyms. Do not fear. They shall be explained throughout the presentation. You also have a reference on that sheet that we provided on the Internet ecosystem. If you flip it over, you have a list of a lot of acronyms, and that's a good reference. Who does what in the technical layers of the Internet, and why this matters to Internet governance discussions. So, for starters, I'm going to show you this news item. That was a bit over a year ago, and Google was basically blocked in France for about an hour. By the end of this presentation, you will understand what happened and why it was so important for the DNS to work properly. What is the Internet made of? It's made of carrots. And by that, we mean that it's not made of sticks. The way that the Internet was built was based on standards and protocols that everybody that wants to be involved in and get into the Internet agreed on. But there are no sanctions. You know, any technical person is free to use the protocol or the standard that they wish. The only advantage is that if you agree to use the agreed protocols and standards, then you get access to the wider Internet. So that's the idea. And that's the concept of standardization. Who governs the Internet? We do, excellent. We do, exactly. It's a multi-stakeholder approach, which is quite unique when you consider the importance of the Internet in our world today. This is, like I said, a bit overwhelming in quantity of acronyms, but we will be covering today. On the bottom, you see all this section in the bottom is a technical layer of the Internet, and at the top is the content layer. And we'll go a bit more into detail. But before we do that, I want to first take you on a bit of a journey on the physical part of the Internet. So the actual infrastructure, what happens physically, what does it look like? And it all starts with your device, laptop, phone, tablet. And what happens when I connect to the Internet? Well, the connection goes to the router. The router is connected to the Internet network within your office or at home. And all those cables will collect and be gathered and go through the wall, all the way down the elevator and into the streets. And the cables are protected, of course, huh? And they will, all those cables that are running all across the streets will gather eventually at junction boxes a bit like this. And that's when we're within the city. But what happens when we want to connect one city to another? Can someone tell me why we have an image of a railroad here? You'll have a little gift if you can tell me why we have a railroad. Yes?
So in many countries, we've used railroads to actually have fiber and a lot of telecommunication cables next to it because it's a really perfect place to put them in.
Excellent answer. Why is it the perfect place?
It's already a path from the major cities to the major cities, so yes, it really helps.
Historically, railroads are the most direct connection between cities. So that's why a lot of the cables between the cities will run. And I'm really bad at this, so... Yeah, oh, not bad. Excellent. So that's between cities. Now what happens if we want to connect between continents? I'm sure you've seen that. Exactly. We have undersea cables. We have a lot of undersea cables, and more over time. This is a map, and this is just an image of the map at a certain point in time, about a month or two ago. It has already evolved, of all the undersea cables all around the world. They are still very important for the Internet to actually work. We saw this in the news about a month ago when one undersea cable was cut and there was the Internet shortage across all the west side of the continent of Africa. Let's just make sure that, to make this clear, that this happens it's very rare now because there's a lot of redundancies. So if one cable is cut, there are plenty of others to take over. So we'll get over that. So this is rare, but still, it reminds us of the importance of the physical part of the internet. But of course, there's not only cable, we also have satellite to connect to the internet, 4G, soon 5G. We have balloons, sometimes even experiences with drones. Those are available, let's say drones, and the balloons and the satellites are still not used very much for internet access because they're still quite expensive, but in emergency situations, they have been used quite a bit. So back to your device. You remember that's where we started from. And what's the end point? Where are we going through all those cables? What's the end point? Well, it's all the data centers. And what do the data centers store is basically the content. It's everything that's on the internet. We often forget it because we use the word cloud to refer to this, but they are very real physical locations where that content is stored. So I think that's something that we need to remind ourselves. There are plenty of examples. Facebook has a huge quantity of data centers. Data centers can be quite interesting as well, just because they produce a lot of energy because of the servers heating up. So there's quite a few of those big data centers that found ways to renew the energy and to cool down, but in a sustainable way. This is an example of a massive data center in South Korea. Not North Korea, I would not have a picture. And of course, we are talking in this case about e-privacy, the free flow of data. And to finish this physical part of the internet, this is just a fun picture of 3 of the founding fathers of the internet. And the image that you see there is the ARPANET, which is the ancestor of the internet. We don't have, unfortunately, the time to go into the history of the internet, but we thought that was so we have John Postel, Vint Cerf, and Steve Crocker. Thank you. And now I give the floor to my colleague Peter to take over.
Thank you, Alex. All right, so Alex took you on a journey across the physical infrastructure. Laptops, networks, cables, copper, waves. But so far nothing is happening. It's just dead infrastructure. So what happens when we start to put traffic on it? The first thing we need to understand is that every device connected to that network needs to have an address. Without that address, it cannot be found. It cannot connect to other devices. And these addresses are called IP addresses. The format that you're most familiar with, because everybody has probably tried to fix a router problem on their Wi-Fi at home, or try to connect a printer. These are IPv4 addresses. They're a format that we're pretty familiar with these days. I'll get to a bit more detail on IPv4 versus the new version, IPv6, in a minute. So where do these addresses come from? There is an organization called PTI, Public Technical Identifiers. They're affiliates of ICANN. We'll get into ICANN a bit later. So but PTI, one of their 3 main functions is managing that global resource of IP addresses. Since IP addresses need to be unique, they need to make sure that they don't distribute it the same IP address to different entities. So your laptop, as soon as it is connected to the public internet, has a unique IP address. And PTI is managing that on a global level by cutting the global resource into regional address pools. So every region gets its own address pool. And on a regional level, they're managed by a regional organization. For Europe, this is RIPE NCC. I'm not sure if anybody from RIPE is here, but there's plenty of RIPE people around at EuroDiG. So if you have any questions on how they set their policies, feel free to reach out to them. So PTI is splitting up that whole pie across the regions. And they send them blocks of IP addresses. So then on a regional level, the organization sets their policies. Who can get blocks of IP addresses? And typically they're members, because you need to be a member to receive your share of IP addresses, or ISPs or mobile operators, research institutions, governments, law enforcement, I think RIPE has over 15,000 members. So there's 15,000 organizations in Europe that receive address blocks from them and then distribute those address blocks to their customers. They can be static and dynamic. And that's an important thing when we're discussing privacy later on. Static addresses are typically used for servers that host content. They are allocated to that server, and they typically do not change regularly. Dynamic IP addresses is that what we, as customers, get assigned to by our ISP. If you know how to find your IP address, for instance, on your mobile, every couple of hours, depending on which part of the network you're on, or you're roaming to a different network, your IP address will be reassigned. And the reason, the original reason for having dynamic addresses, because it seems quite clumsy to always have to reassign an address, is that they wanted to use a scarce resource as efficiently as possible. So rather than have customers not assigning an IP address that they don't use, IP addresses got assigned on a need basis. So when you needed an IP address, you got assigned one. ISPs, or mobile operators, or anybody who assigns these IP addresses to the user level, keeps logs. And these logs, as probably some of you have been engaged in data retention discussions, they're crucial because it's one of the only efficient ways of identifying users later on in the stage. So law enforcement, during criminal investigation, it's exactly these logs that they're after. Which user got assigned which dynamic IP address at which point in time. IPv4 versus IPv6 addresses. By the way, in full disclosure, I'm a lawyer, so I'm not a technical person. Technical people have told me that if you compare the amount of IPv4 addresses with the size of a golf ball, the amount of IPv6 addresses amounts to the size of the sun. So yet again, and I was around 20 years ago, they told us that we would never run out of IPv4 addresses. Now they tell us the same thing about IPv6, but it sounds a bit more believable given the difference in numbers of available addressing there. So the IPv4 address you're familiar with, IPv6 address is slightly more complicated. Benefits of IPv4, it's compatible with old equipment. And old equipment is where you probably least expect it. It's in your cupboard at your home or your flat. It's that old router, old as in more than 5 or 6 years, that can still easily deal with IPv4 addresses, but that is not always compatible with IPv6. Advantage of IPv6 is there are more IPv6 addresses, so we won't run out. There's no scarcity. In particular, developing countries will not face any difficulty in getting more address space. And it has improved routing capabilities, and it's more stable. An interesting aspect of the move from IPv4 to IPv6 is that it is not unlikely that in a few years from now, we'll see less dynamic IP addresses. Because there is abundance, there is no need anymore to assign IPv4 addresses on a need-to-use basis, but you could assign IPv6 addresses permanently to devices and to users. And so that will have a consequence on the logs that ISPs are keeping about their users. So now a bit more in concrete terms. Your laptop, so Alex's story about the infrastructure, it started with a laptop and it ended with data servers. How can we visualize that journey that starts whenever you're typing in a domain name or an IP address or send an email on your machine here? Well, first of all, it's quite easy to identify the IP address on your machine. You look to the properties, and this is for, I think, Windows 9. There's probably Windows 10 here. So you look up the properties, and they're easily identifiable, your IPv4 address of your machine. As an example, I used of data that we're trying to reach in this exercise, I'm using the central website. Anybody has ever tried an NS lookup, and the techies in the room cannot answer that one. So I see a few hands. So there is an easy way of finding the IP address of the content you're trying to reach. That is, if you know the domain name, www.central.org, You can use your command prompt, which is the 80s style interface that still does plenty of useful things, by the way, on your machines. For Mac, it's obviously also available. The command is the same, it's NSLOOKUP. So you do NSLOOKUP, and then you enter the domain name, and it will provide you with an IP address. For the central website, it gives us even two. It gives us an IPv6 address, the top one, and it gives us an IPv4. Frankly, pretty good practice for anybody who wants to publish content online. So now we have two things. We have the IP address of our laptop, which we found by the properties. We have the IP address of the website, which we found through an NSLOOKUP. And we're going to see how both connect to each other. So this is the highest level possible visualization of what the internet looks like. It's a network of networks. So when Alex talked to you about the infrastructure, it was not lit yet. The moment you start seeing traffic on those individual networks, across the street to the crossroad hub, along the railroad lines to the other cities, networks owned by individual operators kind of look like this. So how do they interconnect? And if you zoom in the details, you can see fun stuff here. For instance, there is and it's color-coded, there is a large Asian network, a huge Asian network, actually, basically without any connection to the rest of the internet, could easily be a military network from a major Asian country. So how do these networks connect? Because if you look at this picture, you'll see that there is some parts of the network, and these are the white lines, where many white lines get together. Well, this is an important element in the infrastructure that we shouldn't underestimate it, and it's the importance of the internet exchanges. Internet exchanges are places where your different commercial providers or academic networks get together and literally in one room with their individual server racks across the room, they drag cables across the room to each other. And that's where they peer. And peering is essential because there is no money exchanged in a peering agreement. If even a smaller telecom operator peers with a larger one, they both agree that the value of the traffic, even if it's different in amount, a smaller ISP will send less traffic to the public internet. Even if the amount of traffic is different, they agree that they will not pay compensation. And we all know a different example, another example where it went pretty wrong, basically, and that's the mobile networks. We all suffer from large, expensive interconnection ratings, expensive roaming, because phone networks, contrary to internet operators, do not peer. They have not such agreements in place. So this is what's happening at the internet exchanges. This is a picture from the German one in Frankfurt, one of the larger together with the Amsterdam Internet Exchange. Because of resiliency purposes, of course, the more internet exchanges there are in a region, the stronger the network. If anything happens to one of the operators in Germany or even to the German internet exchange, others in the region can easily take over. It is so good to see that in African countries we see more and more internet exchanges. It also means that traffic stays local. And the huge advantage of that is that it's cheaper. 15 years ago, traffic between two European ISPs typically crossed across the Atlantic back and forth because there was only an exchange between their two networks on the east coast of the US. Whereas now this traffic remains in Europe. It's quicker. You gain a couple of milliseconds of your traffic being sent back and forward. And again, it's cheaper. Relevance on policy and policy discussions of these internet exchanges is the Network and Information Security Directive. More and more core internet infrastructure is considered to be critical infrastructure, and as such, some of the rules and regulations apply. The spread of the internet exchanges across the world, you see that Africa has still a bit of catching up to do, but it's already an enormous difference from a few years ago. And Europe has a very high density of these internet exchanges. So we've explained that trajectory to you. The really fun part is actually that you can see how it works. And the command, so you go back again to that 1880s style command prompt, and you use a traceroute command, trace RT. And you do the same thing. So I'm doing a traceroute to center, trace RT www.center.org. And then the journey starts. And what we've told you so far is visible in that list of IP addresses. So this is in our center office. We're on, the first one is where we connect to the Wi-Fi router. Oh, sorry, the first one is probably the IP address of the machine. We connect to the Wi-Fi router. We get to our firewall. Then we get on the public part of the internet through our ISP called Belgacom. It's even conveniently listed in the name of the router there. So you have both the IP address and the name of the server, which identifies as Belgacom. We hop along the Belgacom network from the router downstairs to the one near the crossroads, to the one near the park, larger and larger, until we'll finally get to that really important crossroad that I mentioned. It's the Internet Exchange. This is the Belgian one, so it's called BNIX. And so here we see that the traffic, that simple trace route that I'm doing, is moving from Belgacom's network to a competitor's network. The competitor is Telenet. It's the largest broadband operator in Belgium. And then on the Telenet network, we start hopping across their hubs, probably zooming somewhere along the railway. We're not crossing the Atlantic because the center servers are in Belgium too, in a city called Ghent. And so there is where a trace route ends. So this is the journey that the packages will make the moment we initiate a connection with the center website. These are all the hubs that the information travels to. So now let's add the domain name system. Why do we need it? How does it work? And the importance of the root and who's managing it. And a quick journey along the top-level domains and their different shapes and forms and policies. That probably, maybe with the exception of Peter, who's, by the way, I should have introduced him. He's hiding behind that pillar there. Peter is the CTO of DNIC and is, no, sorry, you're not the CTO, you're the R&D. Okay. So Peter is our expert who's providing us with technical support for these trainings. And it's always very reassuring for both Alex and me to have him around. So typically nobody can recognize any of those addresses, but there are some of the most used addresses by European internet users. Mine, it's not just IPv4, it's also IPv6. We had an example earlier on. It's not just for web traffic, it's also for mail, which is called SMTP traffic. So it already shows one of the first reasons why we need a DNS. We can remember those addresses. We know where to send an email address without having to look it up. And that's exactly what the DNS does. It's a lookup system. So the first reason, it's convenience for humans. Here an interesting one. It's only recently that the potential of the internet actually got unlocked to more than just about 2 billion people that can read and write Latin characters. What is called the IDNs, the internationalized domain names, got added to the domain name system about just under a decade ago. And we already have 45 different scripts that are now fully functioning. And so here we have our Cyrillic one. Some of you might already have seen Cyrillic addresses. They're not very popular yet. There's a couple of technical reasons for that. There's a problem of universal acceptance, but at least the opportunities are there. And in some Asian countries, they're getting some traction.
Just to mention that IDN names, the names that have Cyrillic or any others, actually have an equivalent in Latin letters. It starts with typically XN / something. So it is possible to actually use them, but they look really bad. So that's probably one of the reasons you mentioned.
Punycode, or what are Punycode? Yes. So remembering the address is the first one. The flexibility of the DNS is the second one. I told you that all machines, all servers, every device connected to the internet has an IP address. But what happens if that IP address is, or the machine breaks down? The place where the machine is held burns down. It happens more than you would think, by the way. In data centers, fires happen occasionally, I would say. Typically, there is data backup. For instance, a large newspaper will not have their data just stored on one server. They have it on multiple servers. But as a user, you just type in the name of your favorite newspaper, and you get to the information that you want, because the DNS translates the domain name to an IP address. However, if that IP address is changed in the background by your operators, as a user, you wouldn't notice it, but you would still easily get to the same information. So your newspaper, one of their servers burns down, they quickly switch the IP address of the domain to their backup facilities, and as a user, you will not see a glitch in the access to information. A third reason is a security reason. The domain name system can help to divert traffic loads. Some of the denial of service attacks can be mitigated partially by proper use of the DNS. And a fourth reason, and it's more a fun one, and unfortunately we don't have too much time to go into detail, but it's related to Internet of Things. And I try to avoid buzzwords during these trainings, but we can't escape it. Internet of Things has a place here. A really cool example is a flood warning system that was built by one of the Centra members running .uk. The organization is called Nominet. And they're using the white space, so the old abandoned TV airwave space, to connect to devices that they stuck under bridges in Oxford. The thing does something very simple. It measures the distance with the water. If that's decreasing, if that distance is decreasing, they know that a bit further down the river they will be expecting floods. And so they're using, they're providing that as open data to the community. Really nice tools have been built with that, for instance, how to avoid traffic jams during flooding times. And where the DNS has a part here is that they have named these devices according to their location for easy reference. And also referring to that, that backup system, so it provides flexibility. If anything happens to one device stuck under a bridge, they can easily switch to an IP address of another device stuck under that bridge. We have a movie on YouTube, on our channel, Central DNS, that explains a bit more in detail on how the DNS works. It's in 2 minutes. And I think you'll really like it. We're not going to play it here. I'm just going to take you through a slightly different version of that explanation. So how does the DNS work? First of all, importantly, and I'll repeat that a couple of times until you're really fed up with it, it's a hierarchical system. And the advantage of that hierarchical system is that it allows every zone, for instance, .eu or .com or .ge, it allows every zone to set its own policy. And that's crucial. It allows for differences or being respectful of local laws, of different needs of local internet communities. A good example is some of the Centra members restrict their zone to inhabitants of their region or their country. .eu is a good example. Only when you're an inhabitant of the EU, you can get a .eu domain name. So it's a hierarchical system that starts with the root. And in that root, currently, there's about 1,500 top-level domains that are held in the root zone file. And then every of those zones manages their second-level zone. So for .eu, I gave a couple of examples. Europa.eu is in there, Eurit.eu, Euractiv.eu. every single domain name ending in .eu is held in .eu's database. And then for the third level, it's again, because of the hierarchy of the system, it's the European Commission, for instance, for Europa.eu, that sets the policies on who can get one. And for Europa.eu, it's obviously only the European institutions. So there's 3 players in this logic. There's the root zone maintainer, PTI, and you'll remember them from the IP address allocation. There's the same organization. In addition to assigning IP blocks, they are also maintaining that root zone. PTI is an ICANN affiliate. For those of you who, around October 2016, were watching the news, something really important happened. It used to be the US government that was overseeing the root zone maintainer. At that point, it was called IANA. And the US government administration decided it was time to hand it over to the multi-stakeholder community, convened by ICANN. So ICANN, the Internet Corporation for Assigned Names and Numbers, organized what, for me, is one of the most spectacular successes of the multi-stakeholder model. They made sure that everybody agreed, governments, end users, intellectual property community, law enforcement, you name it. Everybody who's represented or can be represented in ICANN agreed on a model of oversight of PTI. And that is important because for once and for all, we got rid of the stories that the US government holds the key of the internet. From that moment on, it was the multi-stakeholder community, and they set their policies through the ICANN policy development mechanisms. So that's a key player, the one maintaining the root zone. Secondly, for the TLD itself, we have a registry. And this is, Alex introduced Center as a platform and a group of European country code top-level domain names. This is where our members come into play. They manage the zone for a particular country, whether it's GE or EU, BE or UK. And then on the third level, you have the domain administrator for larger organizations. And in this example, it's the European Commission who's the domain administrator for .eu. And I'm going to use that example through the next couple of slides. So I already share most of that here. So this is what the root looks like. It's probably a bit underwhelming after me underlining how crucial and important it is. But it is actually a pretty simple thing. The importance of the root are more the policies that guide implementation of new TLDs or specific standards that need to be applied. But this is what the root looks like. It's the one in Amsterdam, managed by RIPE. So just maybe briefly on that, there is not just one copy of the root zone. There are 13 identical copies, and they're run by 13 different organizations. It's a resilience measure just to make sure that if one gets into trouble, whether it's organizationally or financially, or there is a maybe hostile takeover even, and there is still plenty of backup. These 13 have then, on their terms, plenty of copies all around the globe. For instance, I think a country like Belgium, just to give an example, has 4 or 5 authoritative copies. I already told you the story about the US government no longer overseeing PTI as of October 2016. This is what a root zone file looks like. It's a flat text file. You can download it. It's available. Not much an interesting read, but I'll just take you through the essence of what it does. So this is the example taken from the root zone file of .eu. And by the way, and there's a prize, an upgrade from the Balls, by the way. It's meant to be one. And you can't answer that one, and Peter can't answer that one. But does anybody know about the hidden dot? The hidden dot? Yes. Anybody cares to explain what it does? There's a hidden dot. Our browser knows that we're inherently lazy. So whenever you type a domain name, you're supposed to add a dot at the end. We never do. But our browser knows, so the browser adds that. You can still try, by the way. If you add a dot, it will still work. Your browser will probably just think that you're a bit nerdy. But there's a hidden dot, and that hidden dot tells your browser to start looking at the very top level when trying to translate a domain name into an IP address. So if you, and you see that dot still in the root zone file. So if you look at the first couple of lines, and apologies for those in the back, it's not easy to read, but it says EU dot. So that's that hidden dot. It has, in this case, .eu has 4, 5, 6, 7, 8. It has 8 name servers. 8 name servers for resilience, of course. They technically only need 1, but they have 8. They can balance the load between those 8 servers. And we'll, in a minute, I'll take you through a journey of how that request works. So, but this is it. This is the root zone file. It has 8 entries for .eu. It has the names of those name servers. It's not very inspiring, but it is X, Y, oh, and then CZ, NL, SI, and UK, which hints where they are located. And then in the second part, it explains where each of those name servers, what IP address each of those name servers are connected to. In the middle, there is a bit of a signature. It's used for DNSSEC. DNSSEC is an additional security protocol. It's a security extension that is added to the DNS. Uptake is still not as good as it should be, but it's improving. And ICANN is doing a fabulous effort in trying to convince more and more ISPs and domain name registrants to implement DNSSEC. It just makes DNS just a little more secure. DNSSEC relies on a signature, a public signature, and that can be found in the root there. All right. Oh, thank you. Yes. There's differences amongst TLDs. You're doing a remote participation, so this one is for you. There's differences in TLDs. There's country codes and there's generic top-level domains. The biggest difference between those two is that policies for a country code are set on a local level. Policies on who can get a generic top-level domain are set on a global level through a multi-stakeholder model under ICANN's umbrella. That's a crucial difference. There is fewer CCTLDs these days than GTLDs. Only changed 5, 6 years ago when ICANN introduced about 1,150 new generic top-level domains. You don't see them too often, but there's a .lawyer and a .car and a .ninja for those who are interested. And there's 311 CCTLDs, more than there are countries, because some of them are these IDN, internationalized domain names that I mentioned. India has a handful for their different scripts. You'll have a .kr for Korea, but they also have the version in Hangul. Japan has 2 or 3 implementations of IDN. So there is more than just countries. CCTLDs are limited. And these 3 guys that Alex showed a picture of, they did something really clever when they came up with the domain name system. John Postel, the one on the left holding the sausages there, was the main architect. And the most clever thing they did was make sure that nor ICANN nor the multi-stakeholders have to decide on what a country is. So they relied on a list that is maintained by a UN agency, the same agency that is managing these ISO standards. And so it's an ISO list, 3166. And there in Alpha 2, which just means it's 2 letters, the 2-letter codes for country codes are maintained. And that's it. It's a limited list. If there is a new country, for instance, former Yugoslavia, split up in 5 or 6 different entities, Then there is a policy development process to add individual CCTLDs to the root zone. But the process before that as to which country codes do they get, and should they get one in the first place? And some of these things are controversial, but the community, probably from a very sound pragmatic engineering perspective, there weren't too many lawyers around at that time, they decided to stay away from that, and with a very good reason. So no discussion on whether Kosovo should get a country code or not. No discussion on whether Taiwan should get a country code or not. Who should get .kr? Is it South Korea or North Korea? The UN is dealing with that, so that's a political discussion that we don't get involved in. Yes, how to get a country code? Well, talk to your local community if you have a new country, and then it will be delegated by ICANN. There is no cost related to having a country code into the root zone. For the GTLDs, that's a different thing. So it's a bit shortcutting, but you can think of it typically as a not-for-profit world, CCTLDs, and a for-profit world, GTLDs. GTLDs are run by commercial entities. And they cost a lot of money. It's about 180,000 euros or dollars to apply for one. And then that multiplies the moment you actually run one. Yes, a couple of examples of policy set by CCTLDs is a local presence requirement. Discussions, interesting, relevant policy discussions for GTLDs is who sets these policies for .wine or point vin in French. The French manufacturers of wines, the guys running the Champagne region, they want to make sure that only they can get Champagne point vin or Champagne .wine. And there's all sorts of interesting policy discussions around that. So I mentioned that our members are managing the CCTLD. So what it does, and this is basically a summary slide just to make sure we're clear on that, provides domain name resolution services. If there is a query for a domain, a .eu domain, then the manager of .eu will make sure that that query gets answered. Runs the hardware, so it's infrastructure, it's redundant infrastructure, there's plenty of copies of the zone file. Typically, CCTLDs work with each other to say, I'll host a mirror of your databases, you'll host a mirror of my databases. Do that all across the globe, and you'll get very quick and very resilient infrastructure. The fourth point, the registration services as such are crucial too, of course. What should you do when you want your second level domain? If you want EuroDiG.org, you talk to a registrar, the registrar registers EuroDiG.org in the database of the domain register, which for .org is a not-for-profit organization run from the US. Managing its own local zone file. Something everybody who's involved in GDPR discussions has heard about, the WHOIS. The WHOIS is managed by the country code top-level domain manager. In Europe, and I'm just taking a sidestep here, we hear and we're often asked at EuroDiG, what do center members think of the ICANN interim solution to deal with WHOIS access? Well, not much actually. Because, as I already mentioned, policies are set on a local level. The ICANN community is not deciding on how the .eu or the .de for Germany should set its policies, so neither how it should set its WHOIS policies. And then there is a bit of billing and contract-related services too. So it's a very technical function. And as Alex said, how to explain to your family what we do and what our members do. The amazing thing is nobody knows about the existence of this quite complex part of the internet ecosystem because it functions. Trust me, if Afnik, who's running .fr, would fail in its job and every .fr domain would be unavailable, even if it's for a couple of minutes. Very quickly, everybody would know what a registry is. But so far, for the last 30 years, they have been doing a perfect job. So I've already talked on how the top-level domain sets its own policies. But let me show you an example of the whois for those who haven't explored that yet. In addition to doing a trace route to figure out IP addresses of name servers, you can go to whois. And then whatever registry, or just type in Google probably whois for a specific zone, and you'll get to the whois interface. One caveat here: this screenshot dates from a couple of months ago, so maybe with GDPR they have updated it. I should change that. So for this one, I've used a specific example. I've asked the whois to give me the data for europa.eu. So who has registered that domain? Where could I contact them? Is there an email address? And these are the responses you get from the whois interface. This is a web interface. There's also a machine interface, which obviously is a bit less exciting to look at. So, but here you see that a guy named Peter Wellens registered the name on behalf of the European Commission. You can contact him in English. His address is one of the central streets in Brussels, and you even have his phone number. This is, I explained the hierarchy of the system. I showed you what a root zone file looked like, a pretty flat file where you have a name server address and then an IP. This is for the second level, identically the same thing. So it just gets repeated every level. Here you have the address for the name servers of europa.eu, a second level domain, and it gives you the IP address. And the Commission does a proper job indeed to have not just IPv4 but also IPv6 addresses. In 1 minute, let me take you through this. I type in a domain name, and this will hopefully bring all this theory together for you. I type in a domain name, and then the query starts. Where can I find www.example.eu? Well, but apparently when we were doing these slides, we were lazy too. So I ask that question to my ISP. That your ISP, if 30 milliseconds ago another user asked, your ISP will already have the answer. But let's assume that nobody asked that question in the last 10 minutes or so. Then your ISP will say, I don't know. And your ISP will start at the top. It will start looking for .eu. Where do I find .eu in your query? So it asks the root zone run by PTI. Where can I find .eu? And PTI sends a response. This is the IP address where you'll find the name servers for .eu. Then the next question gets sent. Where do I find example.eu? And that question is sent to the .eu name servers. Again, you'll get a response. Think of that hierarchical structure in the meantime, right? So you first go to the top level, ask a question, we get a response. It sends you to the second level, you get a response, and then it sends you to the third level, and you finally know where to find www.example.eu. I have an IP address now, and it's only then that the connection starts. Before that, you have no idea where to find that information. Part of it, we give this training, by the way, to European Commission, European Parliament, on a more or less regular basis, 2 or 3 times a year. And one aspect that is always, I would say, the most interesting to some of the people that we're providing this training to, is they have questions on, so now that we know this, how can we use, or how could some use, the DNS to control access to content? If we don't want you to go to your local newspaper, what will happen? What should law enforcement do? Sometimes courts ask us that information too, right? They are in the middle of a court case and they ask technical information how the DNS works. And the one thing they're always thinking of is, can we block access to information or not? So here's the answer. I'm first going to show you what they're trying to do when they're blocking access to information. You could have a court order that says, or a government or a law enforcement agent that tells your ISP that if, I'm taking one slide back, just to make sure that you're not confusing you. If you're asking that question, where can I find this, what is the IP address for the domain I'm looking for, your access provider will be forced by court or by law enforcement agent to tell you that there is no such domain. If in Belgium you're typing in the name of some of the peer-to-peer search engines, whether it's well, Torrent, Hunter, or Pirate Bay. No, Pirate Bay, no, that's another example. But for some of these peer-to-peer websites, your ISP will tell you that it simply does not exist. Well, it does, right? And if you type in its IP address, you'll still get there. But this is a way of the most popular way of implementing DNS blocking, instructing ISPs to lie to their customers. A slightly different version of that is to tell the ISP that it should provide you with the wrong answer. So it should give you an IP address, typically of a law enforcement controlled server, where then you get served one of these notices that you're trying to access information that is considered illegal in your jurisdiction, or anything along those lines. So that's the second way. So not just telling that the domain doesn't exist, but sending you somewhere else. From a technical perspective, this is a really scary thing. The DNS was built, well, the internet was built to withstand a nuclear attack. The DNS was built to be extremely resilient and to give control of each level to the local internet community. This system undermines the reliability of the DNS. Just imagine what would happen if people would not be 100% sure that if they type in the name of their bank.be or wherever their location is, that they would be sent somewhere else. I mean, if you wouldn't be able to trust the DNS, we'd really have a big issue. So that technique where the authorities are actually using the DNS by making your ISP lie is quite scary from a technical perspective. And Peter, correct me here if I'm wrong, but at least a couple of years ago when we started to have those discussions, it was not scalable either. If you do that with a handful, maybe even with 100 names, where you tell your ISP to lie to their customers, that still worked. But it's not scalable if there's thousands or tens of thousands of names. That would be a really bad idea. Importantly, DNS blocking actually doesn't work. I mean, I showed you what they're trying to do, but there's very simple ways of circumventing DNS blocking. The easiest one is just change domain names. I told you how the flexibility of the system is a great way of dealing with any particular technical issue, a fire, a cable that got cut. In the same way, the DNS is a very efficient tool to avoid that type of censorship or blocking. So if you have www.example.eu, well, you just take the Spanish version, ejemplo.eu, or the Dutch version, or whatever you'd like. A perfect example of that technique in practice is, anybody heard about the Pirate Bay? Yes. Swedish courts tried to block it, didn't really work. In the long term, I think they'll make some progress. What happened in most European countries was piratebay.se was blocked by the local ISPs. They got, within a day, at least 50 alternative names. They went from thepiratebay.se to piratebay.se to tpb.se to tbp.org. They suddenly had so many names that they thought it was even quite funny to set up their own, they called it their Hydra website. So every time authorities cut off one of the heads, being a domain name, they had 2 or 3 new that took over. Another reason why, oh no, I'll come to that, I have a slide on that. So I showed you earlier on that it's easy to find the IP address for a domain name. you can type in that IP address into your browser. It doesn't always work anymore these days, since not all content is hosted on dedicated servers. But for instance, if you're looking for the IP address of the European Digital Rights Institute, edri.org, they still have a dedicated server. If they're blocked through the DNS, people can still reach their content by simply typing in the IP address in the browser. So many companies run their own DNS server, resolver. And that led to a really funny situation. I was giving this presentation at the Commission. I tried to show them what happens when in Belgium you're reaching the Pirate Bay, and miraculously I just got to the Pirate Bay. There was no blocking because the European Commission does not answer court orders from Belgian courts. So the Commission obviously runs their own DNS resolver. They're not relying on a local ISP. And so as such, the blocking of the Pirate Bay.se was a bit pointless there. Third-party DNS resolvers. Some of you might know that if you go to your settings of your operating system, you can change your DNS resolver. Typically, it is set to automatically take the resolver of your ISP. So the moment you establish a connection, you get an IP address in there from your ISP, and that is the DNS resolver. You know, that thing that keeps on asking the questions, that will be used. You can use a different one. You can change it, and you can have your preferred DNS server set to something different. The one that everybody remembers is 8.8.8.8, anywhere where you are in the world, and that's Google's resolver. Obviously, there is a price to pay. I'm sure they will be very happy to see all the traffic that you're generating. I think there's also 9.9.9.9 hosted by IBM with a potentially better privacy policy, I would say. So, but there is alternatives. So you can simply change your DNS resolver. So it doesn't ask your local ISP. It asks the third party. And typically they don't oblige foreign court orders. So the conclusions on this blocking discussion, and please take that with you when you engage here at EuroDiG. DNS blocking, it's not an outcome. It's a tool that they're trying to use. It's a pretty blunt tool, and it's a very inefficient tool. And if you talk to, well, I'm sure part of you in this audience qualify, but if you talk to younger people, they know 1,000 ways how to get to illegal content despite DNS blocking. I mean, DNS blocking does not work, and it's dangerous. So it should be the last resort for government or authorities trying to fix a problem. It will never stop users from getting to content that they want to visit. There is one upside to it, that is, it probably stops users from accidentally getting to content they shouldn't be in touch with. Phishing sites are probably a good example, right? There is no point why you would send a user to something that looks like a bank but is not a bank. So that's a big difference. So time to wrap up. I have lost completely track of time, but we're doing quite okay. Alex showed you this picture, and you have a copy on your desk. If you don't have a copy, there is more here. Just wave, and we'll get you one. Interestingly, believe it or not, so we focused on the technical layer of the internet, right? So we promised you that we will tell you the short story of how the internet works. And we focused on the technical layer. What's on top of there is more related to content or governance. It's anything that is not related to the infrastructure. And there is a whole acronym soup below that big red dot in the middle. But believe it or not, we touched upon every single aspect of it. So I'm going to use this one as a guide. No, I'll walk up. That's easier, and I can point. So, and feel free to follow in your things there. On the infrastructure level, we talked about the The network operators, they're the guys running the copper and the fiber and the waves. We talked about the roots servers, PTI run infrastructure. We even showed you that very underwhelming picture there. We talked about the internet exchange points, crucial to strengthen the internet, to create a strong local connectivity between ISPs, making sure that traffic doesn't have to go outside the country. We talked about hosting providers. There was these cool pictures that Alex showed of bunkers in Norwegian mountains and huge data facilities by Facebook. You have the commercial hosting providers, which could be your ISP too. We talked about domain registries, country codes, and generic top-level domains. We didn't do them justice, but we briefly touched upon the standards and protocols. There's a couple of organizations, most of them, or probably all of them, on volunteering basis, with a small secretariat that gets the troops together. W3C, these are the guys that set the standards and protocols for your web browsing activities. They set HTML standards. They set the standards for disability access to specific websites. ITU, we sometimes have the tendency to ignore them in our corner of the world, but international organizations play a vital role in running some of the basic protocols and standards that run the internet, that run mobile networks, that set frequencies, for instance, on which waves you can use. Internet Architecture Bureau and IETF, groups of people that set standards, for instance, the formatting of your IP address, the formatting of email headers, practical things that people need to agree to before that traffic can exchange. They're doing an incredible job, and they're very open organizations, welcoming contributions, although IETF actually has I think a quite expensive entry fee to their meetings, about 400 euros. But you can follow them for free online. And we have, of course, the center reports from IETF meetings if you're interested in what's happening there. So standards and protocols, it's Alex's carrot story. You don't have to apply these standards and protocols. But if you don't do, then you're probably not going to be very successful in connecting to a couple of billion users, but you'll be stuck with your own network. We talked about the RIRs. I only mentioned RIPE NCC. These are the IP address guys. They distribute the blocks of IP addresses to their local communities, such as ISPs and mobile operators. We talked about PTI. We explained that they're in charge of the root zone. So through ICANN, over here, through ICANN they set the policies of who can get .korea in Hangul. But they also deal with the numbers, so the IP addresses that they split off. And they also hold a database of protocols. And this is a pretty technical thing, but it basically means that if as a developer you would like to get a list of time zones or a list of country codes, maybe even, Peter? No? No. Oh, that's an ISO. All sorts of DNS parameters. This is what is being maintained by PTI as well, so that as a developer you have one place where your software can keep on checking those standards. And then we touched upon the naming community. ICANN playing an essential role in there. We keep on telling you that ICANN is a multi-stakeholder initiative. And these are the stakeholders. It's a country code, name supporting organization, us plus quite a few others running CCTLDs or CCTLD organizations. It's a generic name supporting organization. These are the guys dealing with the GTLDs, right? Pretty self-explanatory. But there is also the GAC, the Governmental Advisory Committee. It's all governments. I think they have a membership of about 118 these days. So it's growing every ICANN meeting, I think. So the Government Advisory Committee gives advice from the government to ICANN. ALEC, the at-large user group, any user, typically user organizations that have the resources to send people to ICANN and to participate. So, but ALEC is where you find the users. Security and Stability Advisory Committee, they're the guys that make sure that all these policies actually don't undermine the stability and the security of the DNS system. So they're the fallback. And then, yes, here the regional organizations that are dealing with country codes. We are center, but we have 3 sister organizations. And that's it, basically. So this is it. There is no more secrets. So I'm happy that we managed to take you through that. All right, let me just... So the carrot story, I think it's a very important one, since we have a minute left. A really great example of why carrots work happened in Italy in the 90s. There was one ISP, it was large enough and pretty arrogant because of its size, and it said, you know what, that DNS thing, we're going to add additional domain names. We're going to have a .hotel for our users, and people will register the .hotel domain and build a website for our users. We'll make some money, but then we don't have to abide by these policies that somebody in the US is setting. And so they did, and I think they had about 10 or 15 additional top-level domains that they introduced to their users. So whenever the user, remember that repetitive question thing, whenever the user asked a question to the ISP, it gave its own response. It didn't have to look anywhere. It said, well, our .hotel domain servers, you can find them here. And that worked great until they started realizing that none of the 400 million users at that time in the 90s could actually access the .hotel site. So the people who had registered one and who had spent money on building a website and a payment system and whatever you have, were really annoyed to find out only later that their ISP had basically cheated them into spending money on something that was completely pointless. A .hotel is very interesting for an Italian hotel when you can use the French and the German users and the Austrian users, but the Italian users were not terribly interested. I think .gol, for instance, was another one. So you don't have to stick to the rules, as Tiscali showed us in the 90s, but the carrots, as in access to a couple of billion eyeballs, really works. So we learned that in addition to IP addresses, there is a DNS system and why we need that and how flexible it is, and that we so far haven't messed up. We learned that the DNS is a hierarchical system, again, crucial, because that means that if you want to change your policies of your local TLD, you can do that on a local level. In most European countries, by the way, that policy setting for the CCTLD happens through a multi-stakeholder model. It is far from as delicate and complex as the ICANN one, but typically you would have law enforcement, the users, the business community, and the government sitting around the table before making changes to that policy. And then coming back to the story that Alex shared with you at the beginning and kind of promised that you would probably, hopefully, all understand what happened there. Anybody could, without actually reading it, because it's spelled out there, anybody can imagine what happened? So just to refresh your memories, on a Monday morning, the French Ministry of Internal Affairs went completely black. It was attacked. And at the same time, Google, Wikipedia, OVH, which is the largest French hoster, were unreachable. Anybody could guess? Think of the story that I told you with the lying ISPs. There's another pen. No? When I told it not to mess with the DNS, that actually has a really good reason. Every Monday morning, the French Ministry of Interior Affairs used to send, I don't know if they still do it, this is end of 2016, used to send a list every Monday morning to all French ISPs saying, please block these sites. On that particular Monday morning, somebody probably didn't have his cup of coffee yet, and he sent the wrong list. He sent a test list that, amongst others, included Google, YouTube, Wikipedia, OVH. And they told the ISPs to lie to their users by sending them to a different address, theirs. So they thought it was a really good idea to suddenly have millions of queries per second to Google, millions of questions per minute to Wikipedia and YouTube, to send that to the servers of the Ministry of Interior Affairs, where they should have received a notice saying you're trying to get access to content that is illegal in France. It wasn't, by the way, it was a mistake. So they organized their own DDoS attack against themselves. They committed digital suicide. And they did so because they thought it was a really good idea to use the DNS for blocking purposes. So just in case it was still necessary and to underline, it is not a good idea. Closing down, some corners were cut in this presentation. Obviously, we had an hour and 15 minutes to take you through what I think is a really fascinating story. And there's plenty of material on YouTube and reading. I recommend it wholeheartedly. Thanks to links, the London Internet Exchange, by the way, one of the larger internet exchanges in Europe too, they helped us with these fancy slides on blocking. And that's it. Thanks for us. We still have about 15 minutes for 10 minutes, 15 minutes for questions, if there are any. And if not, you have our IP address, our email addresses, if you want to reach out to us. Any questions? Yes, I think you can use your table mics.
Yeah, I would like to ask about providing country codes with respect to non-recognized or partly recognized state. What is the policy, maybe on example of Kosovo, if you could explain a bit?
The easy answer is I can refer to something I mentioned earlier. ICANN nor other country codes will have any role in deciding whether a country is recognized or not. It's a United Nations issue, and they deal with it practically for country codes, which, by the way, has far more reaching effects than just the DNS, through their ISO lists. So it is not something that ICANN nor, obviously, Centre is dealing with. Any other question? Yes, please.
Could you explain how passive DNS works?
How?
Passive DNS works.
Yes, Peter is great at that. Peter?
So now you know the trick why we are both named Peter. So passive DNS is, I'm sorry. Passive DNS is a technology that, let me start a bit earlier if we have 2 more minutes. So what you see happen is that all these queries for the names with the dots in there and the responses, they go over the wire. And today, all of this traffic is unencrypted. You also have elements in the system, so-called name servers and resolvers, that receive or emit the questions and digest the responses and compile these responses in something that goes back to your computer and into your web browser so that actually the web browser can address something. Now, what is happening that these packets going back and forth, you can eavesdrop on the network. And in that case, the eavesdropping is usually done, it can be done by a malicious actor, but the passive DNS is something where people put sensors in their networks to record the traffic, look into the traffic, and it is mostly done to understand from over time which domain name mapped to what IP address. So that means that over time, these sensor networks will assemble bigger databases saying that www.center.org, for example, pointed to whatever IP or IPv6 address. And well, this is primarily an academic exercise, but it is used in practice to follow up or to understand like malware things. Usually these mappings are kind of static. Like the center website is hosted on a certain web server for some time, then maybe Peter and his team decide to change the provider, and then the IP address will change, and nobody of us will notice because the name remains the same as you explained. In such a sensor network, you would be able, after the fact, to detect that there has been a change. Now, this is not really what they are after. There's things that would probably be far beyond the scope of the exercise here, but there are some like some malware relies on DNS queries, and they will ask, for example, for very strange domain names that don't make sense, that are random strings or something, and that refer to certain IP addresses, which is some botnet systems will be somewhere in the network, and they use the DNS to find their so-called command and control center. So the botnet infected PCs talk to some command and control center, which gives them the instructions to attack systems and so on and so forth. And that is, from the botnet mitigation perspective, it is interesting to find how these things change and who is asking for what, and where are these command and control systems and so on and so forth. This is not, though, an integral part of the overall domain name system. So these systems, these sensor networks are installed by private entities, by some ISPs. There's a large amount of interesting debate around the data protection and privacy implications of all this. And again, it's not an integral part, although it is very much used in practice by people in the cybercrime, or I should say anti-cybercrime, or cybercrime mitigation part. If we want to expand on that, I would suggest we take it offline, not to steal too much time.
Thank you, Peter. And thanks for the question. Anybody else? All right, then we're done. Thank you so much for joining us. I hope you enjoyed it. Bye.